Hi, this is Roger. I am geologist, and here I'm going to tell you the third chapter of my trilogy, which is about Peraluminous arc magmatism. Please enjoy. When I'm speaking about Peraluminous magmatism, I refer to the Ordovician orogenies, which occur in the different Pre-Mesozoic basement units throughout the Alpine belt. Here we have a map of the Alpine chain reaching from Genova in Italy to Geneva in Switzerland to Vienna in Austria. And these Ordovician orogenies, they occur in these light gray shaded basement units. And I did my field observations mainly in the Strona-Ceneri zone, south of the Innsbruck line, which is part of the Southern Alps, but also in the Gotthard Massif, or nowadays called Gotthard Nappe, and in Austro-Alpine units like the Silvretta Nappe and the Ötztal Nappe. If we analyze a type of magmatism, it is important to estimate the proportions. So I did this for these different basement units as they are listed here, from top to bottom. And you see the occurrence of these four lithological formations in square kilometers in these different basement units. And we see that in all of these basement units, the orogenies make about 20 area percentage of all rocks. Now you can say, okay, this is not representative. But it is, because all these pre-Mesozoic basement units are steeply structured. That's why the map view is perpendicular to the planar structures, and that's why the map view is a representative cross-section, and map area percentages correspond more or less to volume percentages of these units. In the previous slide, we have seen that about a fifth of these pre-alpine basement units are composed of orogenies, deformed granitites. Now, analyzing these magmatic rocks in more detail and subdivide them into mafic rocks, intermediate compositions, and granitic compositions, we get numbers like over here for the Strona-Ceneri zone. And what is very obvious is that only 1% of the orogenies are mafics. The others are intermediate or felsic members. A similar pattern can be observed in the Lachlan Fault belt. And that's something I think is typical for Peraluminous arc magmatism in subduction-accretion complexes, that the mafic end members are quite rare. In continental arcs, the mafic end members make about 5 to over 10% of the entire magmatic suites. And for sure, island arc, they have an even bigger proportion of mafic end members. Now, how can we explain these peraluminous magmatic suites with very rare mafic members? For that, I'd like to introduce you to the A-B diagram of Debon and Lefort, two French geologists who developed this chemical discrimination diagram for magmatic rocks. And these two parameters, A and B, they refer to the peraluminosity on the vertical, which means values which are larger than 0. They are characteristic for peraluminous or strongly peraluminous rocks up here, typically sediments. While A values smaller than 0 are metaluminous magmatic rocks. So this is about the content of aluminium with respect to the sum of the alkalis. Along the horizontal axis, we differentiate between leucocratic and melanocratic, or in the chemical language, the sum of iron, magnesia, and titan, which are enriched in mafic rocks. So doing so with different batholiths, we see different patterns. For example, in this bluish area here are the so-called CAFM series. These are magmatic suites rich in calcium and iron and magnesium. And you develop such series when you start with a basaltic source rock, which then is going to fractionate to develop intermediate and felsic granitoids, reaching into the field of peraluminous rocks, but only at its tip. If we look at the orogneses in the pre-Mesozoic basement units, especially in the Strona-Ceneri zone, we see that they plot in this red field here. And as I said before, they are intermediate to felsic, and mafic end members are almost lacking completely. So this must be a different type of magmatism, which is not fully evolving by fractionated crystallization from basaltic source rocks. Instead, the source are sediments with greywacke compositions. A typical peelite or greywacke have such compositions. And we can observe in the field how these meta-greywackes start to melt, producing migmatites. And at a higher degree of anataxis, they develop diataxites and intermediate members to become finally S-type granitoids. So we can observe in the field such transitional stages. What is important is from where do we get the heat to melt such a lot of sediments to produce orogneses which make up a fifth of the crust. From where do we get this energy? And with respect to that, I had a closer look at the banded amphibolite formations, which are down here where amphibolites or metabasalts plot. And there is a distinct gap between the amphibolites and the metasediments or the orogneses. The idea is that this type of peraluminous magmatism is mainly driven by the melting of metasediments, and that the melting is induced by the heat input of basaltic rocks, which are represented by the banded amphibolite formations. Again, this is the AB diagram of Deveau and Lefort. And what I told before is here in a more generalized manner. So we see that metaluminous magmatic suites, typical for continental orgs, they plot about here in the metaluminous field, and they have mafic end members, so typical basalts, and they develop intermediate and felsic members. Peraluminous batholiths, they plot up here. They are mainly peraluminous, can have some metaluminous members, and mafic end members such as basalts or intermediates like tonalites, quartz diorites, they're very rare. The mechanisms behind must be another fractionation which is directed to the composition of biotite. And this is a fractionation which is done by anataxis. So we start melting leucocratic minerals and leave behind melanocratic minerals. So that's why we have a fractionation trend, if we call this like this, which is in this direction, in this AB diagram. So we develop leucosomes with this composition, biotite-rich restites with this composition. And if we start to melt the entire protolith, then we end up again where the bulk composition of the protoliths are. And this is the composition of the orthogneisses. Once we have magmas in this field here, we probably can mix them because they have a similar viscosity at a similar temperature. But we cannot mix a basalt with a melting greywacke. And I will come to this in a later slide, because at a given temperature where the molten greywacke is very liquid, the basalt already started to crystallize and to lose its viscosity. So there is a too large viscosity contrast that we can mix rocks of a basaltic composition with rocks of a greywacke composition. And that's why we mainly transfer heat between these two chemistries. But from a material point of view, we almost cannot mix them. And that's why we lack intermediate compositions between greywackes and basalts. This is a scheme where I compare metaluminous magmatism on the left versus peraluminous magmatism on the right. And in both, you have an AB diagram and also a cross-section through the crust, so from the mow to the surface. What happens in the metaluminous magmatic arc is that you start with basaltic compositions, which come from the mantle. They hit the lowermost crust, and by fractionated crystallization and also assimilation of host rock material, you develop intermediate and felsic compositions, which are typical for a metaluminous magmatic sequence. But if the primary basalts hit the base of accreted greywacke of a super large subduction-accretion complex, then the greywacke start to melt, which is symbolized by these orange colors here. And the greywacke melts, they cannot mix homogeneously with the basalts because they start to cool, providing the heat to melt the greywacke, and the greywacke get very liquid. So there is some intermingling in this basal zone, but the main materials which start to raise and start magmatism and volcanism are mainly of greywacke composition. That's why this type of magmatism has a peraluminous, a greywacke composition. And the primary basalts, as they lose their heat, they start congealing and crystallizing and become solid and stay at depth. Only part of them can raise. And in the AB diagram, this looks like this. We have the primary basalts down here. They hit the greywacke, which melt, giving rise to the peraluminous magmatism. But as these liquids leave the lowermost zone of the accretionary complex, and these primary materials have lost their heat and stay at depth, we have a different magmatism, which has not, like here, a continuous fractionation sequence, but like composition of the sediments these magmas derived from. Let's have a closer look at these banded amphibolite formations. This is a photograph of a hand specimen, a larger hand specimen, which is taken here from a banded amphibolite formation in the middle of the Strona-Ceneri zone, which is located here with respect to the Insubric line, and here is the Western Alpine origin, which starts here at Genova in Italy through Switzerland and continues to Vienna in Austria. Looking at the map of the Strona-Ceneri zone here, it becomes obvious that the banded amphibolite horizon, which goes about here, separates two units, a unit which is composed mostly of mica schists versus a northern unit which is composed of mica gneisses. And look at the orthogneisses, these red and orange types. They mainly follow this amphibolite horizon here. And this map pattern tells something. It tells us that there's probably not only a geometric relationship, but also a genetic relationship. And that's why I had a closer look at these banded amphibolites of the Strona-Ceneri zone, but also I looked at banded amphibolites in the Silretta nappe and other pre-alpine basement units. Here we see the banded amphibolites from the Strona-Ceneri zone, and what is special of this outcrop is that we can observe an interlayering of basaltic layers, orthogneiss layers, again a basaltic layer, again an orthogneiss layer, and so on. So whether these are dikes or if this is an intermingling structure which got deformed, so somehow we have to produce this orthognized texture. So that means this was deformed together, and thinking this deformation backwards and undeform it, we could imagine that we have basaltic materials next to granitic materials in a body, and this is the ideal interlayering structure to exchange heat. So an interlayering structure actually increases the interface, and the larger the interface, the easier it is to exchange heat. So these observations made me thinking about, might these be the remnants of locations where we see the heat exchange from primary basaltic materials towards a material which then generated these orthogneises. Here's a compilation of further field observations. This comes from the Silvretta map, where I could make exactly the same observation of an interlayering of sheets of orthogneises within sheets of banded amphibolites. Or here we can observe how augengneises are associated with amphibolites. And especially at locations here in the R massif where the deformation is not strong, we can observe the original contact between a basaltic material which came in contact with a meta-gray-wacky material. And we have clear indications of a reaction rim across which the two materials exchanged not only heat but also fluids. And probably these are the outcrops where we can observe how a hot material intruded a gray-wacky material which started to melt, but we could not mix the two materials, so they stayed separated. But we have a clear indication of reactions between the two. This is part of the official geological map of Switzerland. You can access this map on the internet, and it shows a section in the Lötschental, which is in the Wallis in the south of Switzerland. And here we see the Pre-Variscan basement, which is an interlayering of steep sheets of banded amphibolites intercalated with migmatites, here in M, paragneises in P. And sometimes these banded amphibolite formations are associated with ultramafics, indicated by these stars. So how can we generate such an assembly of an intercalation of orthogneises, paragneises, migmatites, and banded amphibolite formations? That's the key question. This is another example of a banded amphibolite formation from the Silvretta map. This spot is about 200 meters thick, and it's a nice example how large the variety is of different lithologies within this one and the same banded amphibolite formation. So we have metagabbros, we have intermingled rocks, like we see here, of basaltic schollen within a gabbroic matrix. We have banded amphibolites like shown here, so this comes from over here. the bands are from millimeter to centimeter scaled. We have former septa of porognises which became metamorphosed and show large garnets and also micas and hornblende contained in these gneisses. Or we have again multiple layers of basalts which are intercalated with porognises. So there's a large diversity of rocks within these formations. This is a very important scheme. With this scheme, I like to visualize what I mean with intermingling. So I defined this zone of intermingling, which is at the base of an accreted pile of greywacke. And below here we have the basalts, which derive from the mantle, and they hit the lowermost greywacke, which immediately start to melt. And these melts are being mobilized along transpressional shear zones, which, by the way, structure and steepen the planars, the schistosity, the lithological contacts. And these transpressional shear zones, when they open gaps, they soak in the magmas from deeper levels. And that is the mechanism which produces these peraluminous orthogneiss sheets. Now in this model, the banded amphibolite formations are intermingles of basalts and greywacke magmas, and these interminglings are from time to time also soaked into gaps of shear zones, and they solidify and are myelinatized, and this, I think, is one way to produce banded amphibolites. This mechanism would also explain why we have zones where these banded amphibolite formations occur together with sheets of orthogneisses. And the reason we produce these interminglings is simply because the liquidus of a peelite system, of greywacke system, is about there where there is the solidus of the basalt, of a mean basalt. So that's why these two materials cannot mix. They have different viscosities at given temperatures. And that's why we mainly exchange the heat at the moho, but not so much the material. And that's why we do not evolve these materials to generate a metaluminous magmatic suite, but we transfer the heat of these primary basalts to the peelites and greywackes, which then from a material point of view are the material from which we produce the orthogneiss. And that's why we lack, or not completely lack, but why the mafic end members of these magmatites are rare, because they remain at depth, because they are heavier. And in some cases, we soak in these interminglings and produce banded amphibolite formations. That's the model I have in mind when I'm speaking about the relation between banded amphibolites and peraluminous orthogneisses. I mentioned several times transpressional tectonics, and this is a very important topic when we speak about cratonizing subduction-accretion complexes, because the direction of subduction is very often not perpendicular to the coastline, and that's why subduction is in most cases oblique. And that's why we produce zones along these shear structures where we have compression, like here, but also zones where we open gaps. And these gaps you can fill either from above, so we have Cenerian basins where we can fill in gray wackies, for example, and readily deform them again in the next phase of the same orogenic event. Or we can fill them from below with magmas near the moho, where they are generated by the intrusion of primary basalts. And by this mechanism, we create a system which operates along steep shear zones, and we bring deeper materials to shallower levels and vice versa. And this is the main mechanism which results in a cratonized crust. So the accretionary complex, which is about 20 to 25 kilometers thick, which starts to melt at its base, and where these magmas are transported along steep fault plains to higher levels. This is actually the mechanism to cratonize the complex, and by that we create a crust which is between 20 and 30 kilometers thick, and this is isostatically stable, so there is no driving mechanism for uplift and erosion, and that's why these complexes remain as they are generated. So that means the lower crust remains at the lower crust, the middle crust remains here, and what was at the surface when it was generated stays there. So in the Lachland Fault Belt, we observe this shallow scenario, whereas in the Strona-Ceneri zone, we have an insight what happens in a similar origin in the lowermost part of an accretionary complex. This is the most complicated scheme I have drawn, and I published it in the paper of 2020. It shows a cross-section through a cratonizing subduction-accretion complex in the early Paleozoic at the periphery of Gondwana, like for example during the Cenerian Orogeny. We go to a depth of 100 kilometers, and around here we start to produce eclogites which are associated with banded amphibolite formations, for example. But before I go to further details, let's have a look at the legend down here. All the arrows, they indicate how the materials flow, in what direction. So we have different flow, for example, of the oceanic plate downwards, or the lithospheric mantle coming in here from this side here. And also it is possible that we bring in asthenospheric mantle, which is very important because we grow these complexes and we must fill the space underneath. And one possibility is to thin the lithospheric mantle. Another possibility is to bring in hot asthenospheric mantle. And both is possible. For that reason, we can generate different types of basalts. Basalts generated by fluid flux related to the subduction, or basalts generated by the decompression melting of asthenospheric mantle. Here we see a list of possible protolith of banded amphibolite formations, which were generated from basalts or from andesites, which are associated also with ultramafic rocks. And here is a detail to understand all these drawings along the subduction channel. Now what is important is that, as I said before, the basalts which hit the lowermost part of the accreted greywacke, they can have different compositions. And that is very important if we analyze basalts on their chemistry. But I will come to that in a later slide. And this is what I have explained before. This is the intermingling zone where I produce the peraluminous magmas by melting of greywacke, and intruding them is the mechanism to produce sheets of orthogneisses along these steep reaching transpressional folds. And if intermingled magmas access such a structure, we produce a banded amphibolite formation. The same information from the previous slide can be drawn in a pressure temperature diagram. So we have here the subduction channel where we subduct greywacke to great depth. Also the oceanic plate goes down here where we produce the eclogites. We have also asthenospheric mantle which can come in and fill the space underneath the growing accretionary complex. But we have depleted lithospheric mantle which experience this fluid flux related to the subduction which starts melting. So we can produce calc-alkaline basalts but also tholeiitic basalts in the same environment. And all these basalts, they hit the accretionary complex, and down here we produce greywacke melts. And if we calculate how much greywacke we have to melt to produce the entire volume of orthogneisses, we must assume that about the lowermost 6 kilometers of the accreted greywacke must melt completely. So we need a lot of basalts, about the same amount of basalts we need to melt a similar amount of greywacke. The eclogites, they can be transported with melange diapirs very quickly without being heated too much into this zone, and most of them are probably then equilibrated thermally and they become amphibolites, ordinary amphibolites. But if they go quickly into one of these channels, or especially here with an intermingling which is soaked in a shear zone producing banded amphibolites, that is a possibility that we can associate ultramafics which are transported from eclogitic depth to the intermingling zone, taking the next elevator, going with the banded amphibolites being sheared into shear zones and reaching intermediate and higher levels in the accretionary complex. So this is the mechanism that explains why ultramafics and meta-eclogites are associated with banded amphibolite formations. If we analyze the amphibolites from the Strona-Ceneri zone, then we see that some of them they plot into the tholeiitic field and some of them they plot into the calc-alkaline field. But we should not go and take this line too strictly and say, okay, we have morph signatures and we have arc signatures. Because as we have seen in the models before, we can have different mantles involved in the mantle wedge below the growing accretionary complexes. And that's why I could imagine that we produce basalts of different sources, producing at the same time calc-alkaline and tholeiitic basalts. Again, we have to be aware that we should not apply classical chemical discrimination diagrams which were developed on the base of existing tectonic settings. As I said, for the discrimination of Peraluminous granitates. So the same is valid. The same skepticism is valid for the mafic rocks. This is a scheme to visualize how you can make banded amphibolite formations from different protoliths. So you can have basaltic dike swarms intruding paragnesis, or you can have intermingling of more mafic with intermediate or felsic magmas, or you can also take a tectonic melange, or you melt older banded amphibolite formations and deform these magmatites again, or also the backveining of cooling basalts which provided their heat to gray wackies, and as these cooling basalts shrink, you can make cracks and backvein the gray wacky melts into the basaltic rocks, and also produce composite protolith, which then, when they are going to be deformed, so these red arrows are always a deformation, you then produce banded amphibolites. So this is a cross-section through a Paleozoic cratonizing subduction-accretion complex at the periphery of Gondwana. Could be in the Lachlan Fault Belt, could be in the Cenerian Belt north of Gondwana. And this here is an enlarged section showing the region where the primary subduction-related basalts, whether they are produced by fluid flux melting or by decompression melting of incoming asthenospheric mantle, as these basalts hit the lowermost accreted gray wackies, and we have large-scale regional melting. We can have both. We can have fractionated crystallization producing still metaluminous batholiths, but we can also produce peraluminous batholiths when only the heat is transferred at the moho, but not much of the material. This model shows another detail which I did not discuss up to now, that probably the upper crust or the upper parts of such an subduction-accretion complex shows a different PTT path compared to what happens in the lower crust. So at the same time as we have high temperature, low pressure metamorphism related to the heat which is transported by these orthogneisses into the uppermost crust, we have high pressure, high temperature metamorphism in the lower crust. So what we observe in the Lachlan Fault Belt, because the Lachlan Fault Belt is exposed at its original surface, there the geologists observe mainly high temperature, low pressure metamorphism, regional aureoles, or they call these granites regional aureole granites. But in the Strona-Ceneri zone, we have today the lower crust exposed because we had an overprint during the Variscan and Alpine collision, which turned part of these basement units upside down and pushed them to higher levels. So we can study today the lower crust, which was generated in the Ordovician, we have a completely different metamorphic story. So the two metamorphic imprints occur at the same time. And the big difference to normal orogens we are used to, we are taught in the school, is that these orogens, they operate along steep structures, whereas nap piles of collisional orogens work along horizontal structures, horizontal folds. Here, when we move a magma or a rock 10 kilometers, then we are 10 kilometers higher or 10 kilometers lower. If we push an alpine nap by a distance of 10 kilometers, then maybe we are 1 kilometer higher up in the crust, but not 10. And that's why these systems are so effective, because material transports are vertically organized and we very quickly exchange material. And that's also the precondition to cratonize in situ the entire crust. One of the take-home messages of my presentation is summarized here. If we are dealing with subduction-accretion complexes, like here, quite a small one, as we can observe it today in the Gulf of Alaska, we have to be aware that these greywackies, they come from a hinterland, for example, from a volcanic arc, which has a given signature, like a volcanic arc signature. And the greywackies, which are deposited here and being accreted, they inherit the same signature from the rocks they derived from. The same occurs when these greywackies are being subducted to be metamorphosed and become paragneses. They still have a volcanic arc signature. And when these paragneses are going to melt to produce orthogneses, again, the same signature goes into the orthogneiss. So the volcanic arc signature of the orthogneiss is not indicating its tectonic environment, but it's indicating an inherited signature which was inherited from a sediment, which was inherited from a volcanic arc in the hinterland. So that is a main aspect we have to keep in mind when we are dealing with subduction-accretion complexes, which are huge recycling systems. So we cannot go into the field and take a sample of a granite and analyze it and say, oh, it's a volcanic arc signature, so this must be a volcanic arc granite, or taking an amphibolite and come out with a morph signature and say, oh, it's a mid-ocean ridge. We have to be aware that we have a very dynamic tectonic setting where we might fail with the application of standardized chemical discrimination diagrams for magmatic rocks. And this citation comes from the paper of Barker et al., which I really can recommend to read because it really inspired me to get used to a critical application of chemical discrimination diagrams. To summarize, I again start with the Andean setting, where we have a metaluminous arc, continental arc, related to the subduction of an oceanic plate, we have a small and cold accretionary prism. And when we do a chemical analysis of these granitoids, we see the composition of a metaluminous sequence in an AB diagram of Dubon and Lefort. Now, if we increase the sediment flux and these accretionary complexes start to grow and they become as large as they were in the early Paleozoic, then we result in a setting where the arc is entirely within the accretionary complex, far away from the rim of the craton. And that's why we don't fractionate the primary magmas to evolve metaluminous granitoids. We only transfer the heat and we generate peraluminous magmas by the melting of gray wax. And that's why we change the composition from this signature to this signature. So understanding peraluminous arcs is very important in the context of Paleozoic subduction-accretion complexes, which cratonize in situ during peraluminous magmatism. About 20%, 20 volume percent of the accretionary complex must melt to produce the amount of magmas we need for the orthognosis. And together with the other observations, having the fleischoid sediments, the steep structures, we have aclogites, and we need tectonics to produce these sheets of orthognosis. The model of cratonizing subduction accretion complexes, I think, is a valuable contribution to a better understanding of these gneiss complexes we can observe all around along the periphery of Gondwana. This is my last slide. It's like a graphical abstract, and in one sentence we can summarize everything. And it says, we have a high sediment flux to active margins, and this caused the recycling of this crustal material at the periphery of Gondwana by the cratonization of subduction accretion complexes during peraluminous magmatism. I hope that I could inspire you by my presentations, and I would be glad if you could share some of my ideas with others, also to critically discuss them, and who knows, maybe we meet each other and can discuss personally what's about these concepts and ideas I gained from others and reapplied to observations I made in the field. Thank you very much for your interest, and I wish you all the best for your studies.